So what we're going to be doing today, we're going to do a few more examples on operational amplifiers. Just make sure we all understand exactly like what's going on, how we can approach any circuit with an op amp in it. And then we're going to move on to like one of the most important things that we learned in this class, which is called Thevenin equivalent circuit or Norton equivalent circuit. We're going to talk about like those things, and we're going to say, okay, if you have like this very complicated circuit, how can we replace that complicated circuit by something that's easy so we can actually work things out quickly? Okay. So let's start off by just talking about like a few more examples on op amps. Example. Let's just say I'm given this circuit. This is the input voltage that's connected to the ground, followed by two resistors, 100 ohms. The other one is 150 ohms. It's connected to an op amp. Positive side is connected to the ground. And we have two resistors with values 9K and 18K in parallel. The whole thing goes to the output. And this is the out. And this question is asking us, what is the gain of this circuit? This is another way of asking what is the ratio between output and input. Okay, this translates to what is V out over V in. Right? If we're given any circuit with op amp, we're going to check if it's ideal or not. If it's ideal with negative feedback, then we have like golden rules of op amps. We can apply it, and then we can do KVL and KCL and solve for whatever the question is asking. This circuit is telling us the op amp is ideal. It tells us this op amp is negative feedback. It is because it's going from like the output to the inverting terminal. So I have like golden rules. So golden rules of op amp, what it tells us is that if I look at this node over here, call it V plus, look at this node over here, call it V negative, we know V plus must be the same as V negative. We know that, right? And we also know if we call this current here I negative, this current here I positive, I negative must be the same as I positive, and that must be 0. Right? So I can use these two rules that I have, apply it to the circuit, and find the ratio of V out over V in. Right? I can do that. But if I look at this circuit, this is a familiar circuit to us. I know exactly what the gain is. What is this circuit? Let's just assume I combine these two, which I can, and I combine these two. What is the circuit? It's an inverting op amp, right? It's an inverting op amp. And if it's an inverting op amp, I know exactly what the gain is. What is the gain? The gain is negative of this resistance, which is the combination of these two, over this resistance. Right? So I know exactly what the gain is. So the gain, which is V out over V in, is negative R2 over R1. And this is for inverting op amp. What is R2? This is R2. R2 is 18K in parallel with 9K, which is a 6K. R1 is these two in series, which is 100 plus 150, which is 250 ohms. Right? If I divide them, it is minus 6,000 divided by 250, which is negative 24. Right? What is the unit for the gain? What is the unit? I'm dividing two voltages. So the unit would be volt over volt. Right? Right? So what did I use here? I basically identified this circuit to be an inverting op amp. And I used basically the formula that we had for the inverting op amp. Right? It could have been like non-inverting op amp, which we knew the gain would have been like 1 plus R2 over R1. Right? But this one is inverting, so it's minus R2 over R1. We know it, we can just use it, and we get the gain. If we did not remember this formula, again, that's not a big deal. We can still apply the golden rules. We know current through R1, which is the combination of 100 ohms and like 150 ohms, is exactly the same as the current through 9K and 18K in parallel, right? Because there is no leakage at negative terminal, right? I negative is 0. So we could use that fact and write a KCL there to find I through 18K and 9K in parallel. As soon as I know current through that, I know voltage across it. And given that, I could basically find V out. Right? If I don't remember, I can do that. But this is a known circuit. Any question on this? Is that clear what's going on? Yes? Let's make it a little more interesting. Let's just say I am given this circuit. Example. I have this input voltage. This is V in, connected to R1, connected to R2. And then this is connected to an op amp that looks like this. This is RF. This is RI. And over here, I have the out. Right? And the question's asking me find the gain. Right? Again, this is an ideal op amp. So we know golden rules hold if this is a negative feedback. It is a negative feedback because we're going from the output to the negative terminal. Right? Let's apply golden rules. Supplying golden rules. What do we have? We know if we call this thing over here V plus, this thing over here V negative, V plus must be the same as V negative. So the first rule is V plus is exactly the same as V negative. The second rule tells me if I call this I positive, this guy I negative, I know I plus must be the same as I negative, and that must be 0. I know that, right? What else do we know? If you look at all these grounds, they're all the same, right? So what is voltage across both RI and RF? Well, voltage at this node, what is it? It's V out. Voltage down here is the ground. So the difference here is V out. But this ground is exactly the same as this ground, right? So do you agree voltage across both these is V out? It is, right? But what is this I negative here? That is 0 because of this rule that we have. Therefore, I know these two things are in series, and voltage across both of them is V out. So what is voltage across Ri? That's a voltage divider, right? So I know voltage across Ri. It's a voltage divider. Which tells me that should be Ri divided by Ri plus Rf times V out. Right? So far, you with me? Does that make sense what's going on? But what is V across Ri? Do you agree V across Ri is exactly the same as V negative? It should be. Why? Because this is V negative. And this is exactly the same as this guy. It's the exact same as voltage at this node. Right? Because there's just like wire there. There is no voltage drop. So do you agree this is exactly V negative? Right? But the first rule that we have implies this V negative must be V positive. Right? So this is the golden rule 1. What does that tell me then? It tells me V positive over here is this guy. But what is V positive? Do you agree V positive is voltage across R2? Again, this is V positive. It's the exact same as this. Right? So V plus minus 0 is voltage across R2. Right? So I have V plus equals voltage across R2. But look what I have. Voltage across both R1 and R2 is Vn. Why? Because again, this is the same ground. Right? So what kind of circuit do I have over here? What is it? It's a voltage divider. I have two resistors back to back. There is no current leakage over here. They're back to back. I know voltage across both of them is Vn. What is voltage across R2? It's R2 divided by the whole thing. So again, this is another voltage divider, which tells me that should be R2 divided by R1 plus R2 times Vn. Right? But we already computed a V plus. We know V plus is this. So I'm going to just plug it in here. V plus is Ri divided by Ri plus Rf times V out. And that should be the same as R2 divided by R1 plus R2 times Vn. Remember, this is V plus. Now I know the relationship between V out and Vn. I can divide this by Vn, and I get the relationship that I want, which is my gain. V out over Vn is R2 divided by R1 plus R2 times Ri plus Rf divided by Ri. This thing over here is 1 plus RF over RI. Right? It should make sense to us. Why? Because if I look at this portion of the circuit, assuming this doesn't exist, what is this circuit? It's a non-inverting amplifier, right? And the gain for a non-inverting amplifier is this guy, is 1 plus RF divided by RI. But now I hooked it up to another circuit that implies exactly what the input voltage to this non-inverting amplifier is. I have to adjust that value by R2 divided by R1 plus R2. Right? But this is essentially a non-inverting amplifier. Right? So let's just have a quick recap of like what we're doing whenever we have a circuit with an op-amp in it, or more than one op-amp in it. As soon as we identify that the op-amp is ideal op-amp, we know the golden rules hold. The rest is just choosing a method that we like. I use a lot of like, current divider, voltage divider. You don't have to. You can do like KVL, KCL. You can do Norton analysis. You can do mesh analysis, whatever method that you like. And apply the constraints that we have due to op-amp being an ideal op-amp, and then solve for the out or the whatever the output is, or find a gain. Right? So whenever you're given a circuit with an op-amp in it, the first thing you check is to see if the circuit has ideal op-amp or not. If it has an ideal op-amp in it, you're going to apply the golden rule, and the rest is just writing KVLs and KCL. Right? Does that make sense to everybody? Yes? You guys back there? Does that make sense what's going on here? Yep. We good? Is that understood? Should we move on to something new? All right. Now we got that out of the way. Let's talk about something very, very useful. Let's just say you're working for a company and your boss gives you like a very huge circuit with a lot of dependent sources, a lot of, independent sources. And your boss asks you to find something in the circuit. For example, voltage across an element, current through an element, right? You're just going to be like, oh, yeah, OK, I can do this. You're going to write your KVLs, KCLs, whatever method you want. And you're going to find that value. You're going to give it to your boss. And he's like, oh, I'm sorry. I didn't mean to ask for this resistance, for example, or this element. How about we change the value to this other value? What is the voltage across that? What do you do? Just going to be like, OK, fine. I'm going to write my KV and KCL again. It doesn't matter how complicated the circuit is. I'm still going to find it. I'll give it to you. Right? You're going to come back to your boss and just be like, hey, this is the answer you wanted. Now, let's just assume that boss is me, and I'm a horrible boss. I want to torture you. I'm like, oh, no, you know what? How about this value? Yeah, you're going to shake your head just like him, just like, what are you doing? Right? But you're going to have to go back and try to solve the circuit and come back to me and just be like, hey, this is the answer. And again, I can just torture you again. And this can continue. What if we could just simplify that very complicated circuit that we had into very, very simple circuit around that specific element that I am interested in. So that whenever I want to like solve for whatever value that I'm interested in, instead of solving that huge circuit with a lot of dependent sources, independent sources, I only look at that very small, simple circuit. Basically, what if I put all those very complicated things, all those elements, in a black box, and put the element of interest in this little box? Let's just say this is, for example, a resistance RL. Right? What if I could, let me just write down, this is very complicated circuit with a bunch of dependent, independent sources in it. Right? What if I could replace that black box by a simple circuit I know? For example, a voltage divider or a current divider. What if I could do that? Then my life would have been much, much easier. Right? So the question here, or our goal here, can we replace the black box by a simple circuit such that the external behavior of the black box remains the same? Again, I don't really care what's going on inside the black box as long as I know what's going on here. Let's just call it A and B. As long as I know voltage across A and B or current through here, right? I can solve for whatever I want about this RL, right? So if I replace this black box by a simple circuit that gives me exactly the same as voltage across A and B and this current, then I'm good to go, right? So my goal is to replace that very complicated circuit, right, with a very simple circuit, very, very simple circuit that has the external behavior exactly the same as this one. Particularly, we aim to replace the black box by one of these circuits, because these are the simplest circuits that we know. A voltage source, let's call it Vs, followed by a resistance, or a current source in parallel with the resistor. So this is basically my black box. And this is going to be A, this is going to be B, this is going to be A, this is going to be B. And my hope is that if I look at A and B, if I look at voltage across it or current through it, that's exactly the same as A and B over here. So this is going to be like my black box. Right? If I can do this, then my life is like much, much easier. I can stick that RL back in here, right? And no matter how many times I change my mind about RL, it's just a very simple calculation. You can find voltage across it, current through it, It's very, very simple calculations, right? You don't have to like solve the circuit from scratch again, right? So if I can have like this circuit, I can stick this RL back in here, right? And this is either like a voltage divider or a current divider, and I can solve. But here are the questions we should answer. The first question is there any circuit like this or like this? Does such circuit exist? That is the first question. Second question that we should answer is that assuming it exists, what are these values? What is Vs? What is Rs? What is this Is? What are these values? How can we compute this? Right? So these are two main questions that we should answer. Before we answer like those questions, for a second, let's assume like these circuits exist. We still haven't talked about like the existence, but let's just assume it exists. Okay. So assume such circuit exists. What do we have? I have like this black box. That's connected to some RL. This is voltage here. This is I here. And we know we can replace this black box by either a circuit that looks like this or a circuit that looks like this. Right? This is what we know, assuming it exists. I haven't answered that question yet. Right? If I wanted to find Vs in this circuit, how could I do that? Do you agree if I leave these two terminals open and if I compute voltage here, this voltage is exactly Vs? Why? Because this is open. There is no current going through this. So whatever voltage I have here is just going to jump across this. Right? So Vs is V open circuit. What it means is that if I replace the black box by this circuit, to have like the exact same external behavior, I have to go back to my original circuit, remove whatever is in between A and B, and find V open circuit there. And since these two circuits are supposed to be exactly the same, this Vs is V open circuit. How about here? How can I find Is over here? What I'm claiming is that if I look at AB and then short it out and call that I short circuit, Is is exactly this I short circuit. Why? Current always takes the path with the least resistance. So instead of going through this Rs, it's just going to go through this wire over here entirely. So Is must be I short circuit. And if these two circuits are supposed to be equivalent, they should have the exact same external behavior. And to be able to achieve that, we're going to have to go back to the original circuit, remove whatever that goes between A and B, replace it by a wire, and I short circuit must be that source value. Right? Again, this is just my black box. This is my black box, and this is my black box. Right? So that's pretty good. But we have a fundamental question. Does such circuit exist? Can we actually do this? The answer is yes. So let's just write that down. Question 1. Does such circuit exist? As I said, the answer is yes. And the reason why is the following theorems. Theorem 1. Any circuit with dependent sources, independent sources, independent sources, with a bunch of resistors can be replaced by a circuit with a single voltage source followed by a single resistor. So pictorially, what it means is that I have like this black box over here, which is connected to some element, right? I can replace this black box by a voltage source, Vs, followed by a resistor Rs, such that the external behavior of this black box is exactly the same as this little circuit over here. And if they're exactly the same, I can basically put this element back in here. Let's just call it like RL. Right? This is called Thevenin equivalent circuit. I briefly mentioned how I can compute this Vs, right? But I still haven't told you how I can compute Rs, right? This theorem only tells me I can do this. I can replace this black box, no matter how complicated it is, by this very simple circuit. And if my boss comes back to me and asks me to change RL, I can simply do it without redoing this circuit, because the external behavior of this black box, whatever is happening outside this black box across that RL, is exact same as the external behavior of this little circuit, which is the voltage source followed by a resistor. Right? Not only that, the second theorem tells us we can replace this very complicated black box with whatever is inside of it with a current source in parallel with the resistor as well. So let me just write it down. Theorem 2. Any circuit, again with dependent and or independent sources, with a bunch of resistors, can be replaced by a circuit with a single current source in parallel with a single resistor. Right? And pictorially, what it means is that I have like this black box. It can have anything in it. I am not really interested in what's going on inside this black box. All I care is what's happening outside this black box. Let's just say it's connected to RL. We can replace this black box by a current source with value IS, followed by a resistance in parallel with it. And if I look at this A and B, the external behavior of this very simple circuit is the exact same as the external behavior of this black box. Right? This is called Norton equivalent circuit. Right? That's pretty nice, right? Because this black box can be very, very complicated. Right? I just need to solve it once to get IS and RS. I can plug it in there, and that's it. Right? So the idea here is that I have to determine that VS, that RS, and this IS such that the external behavior of the black box remains the same. Right? So that's what we're going to do. So idea here, determine VS, IS, RS such that the external behavior of the black box remains the same as the equivalence. Right? If I can do this, if I can determine like these values, I can throw out that black box, and I can only work with this little circuit that I have over here without even worrying about what's going on inside this black box. Remember, I don't care what's going on inside this black box. It imposes like some conditions on the variable of interest, in this case RL, right? But besides that, I don't really care what's going on inside of it. All I care is what are the conditions that this black box is imposing to that RL. And that's basically the external behavior of it, right? As soon as I know the external behavior, as soon as I can determine that VS, IS, or RS, I can throw out the black box, and I can only work with this circuit. And now I can answer all the questions about RL, right, without having to go back to the original circuit and try to solve for those things, right? So that's pretty neat. That's pretty nice, right? But the question is how? How can we do that? Any question on these things before I try to motivate it a little more? Any question? Is that clear why IS must be I short circuit or not? Is that clear to everybody? Yes. Sure. So let's just basically walk you through both of them, right? Let's see what we have over here. This is the black box that we have, and this is the variable of the interest. This is basically the element that we want to find something about, right? The idea is that I'm going to replace this black box by a circuit that looks like this or a circuit that looks like this. Let's focus on this one first. Do you agree if I leave these two terminals open, there is no current that's flowing through this guy, right? And therefore, whatever voltage I have across A and B must be the same as Vs, right? Just writing in KVL tells us. But remember, this little circuit over here is a representative of this black box, right? So if I remove this black box and replace it by this guy, it should have exact same B open circuit, right? So if I go back to my original circuit, since I want to have the exact same external behavior, if I want to find this Vs, I have to remove this element of interest and leave it open and find voltage across it. Because that voltage across is exactly voltage across these two terminals, right? Therefore, my Vs is indeed V open circuit, which I find it in the original circuit, right? How about over here? If I find current through A and B just by shorting it out, I know Is must entirely flow through this branch, right? Because current always takes the path with the least resistance. So Is is entirely going to go through this I short circuit. And that must be basically I short circuit. And since this little circuit over here is a representative of this black box, I short circuit over here must give us this I of source, right? Is that clear what's happening? Yes. Correct, yes. Right? Or another way of saying it is that, like, if I have terminal A and terminal B here, I leave terminal A and B open, or I basically short it out. That's another way of saying it. Right? I still haven't told you how I can find Rs. Right? One way of doing it is like very simple, right? I know this circuit, and I know this circuit. I know not only are these circuits equivalent to this black box, but they're equivalent to themselves, because they're representing exact same circuit, right? So the external behavior of this circuit must be the exact same as the external behavior of this circuit, right? So if I want to find this Rs, it turns out I can just divide Vs by Is. I'm going to walk you through it entirely next lecture. But just because of these two circuits being equivalent, I know Rs must be Vs over Is. We're also going to learn a shortcut for like very special cases to find this Rs. But in general, since these two circuits are exactly the same, because they're representing the exact same black box, so the external behavior of them, if I look at A and B and the current divider version, and A and B in the voltage dividers version, they should represent the exact same thing, right? And given that, I can compute that Rs, which it turns out to be that Vs divided by Is, right? We're going to talk about it in detail. For now, we only know how to compute Vs, which is V open circuit. We know how to compute Is, which is I short circuit, right? But let me motivate this a little more. Motivation. Let's assume we determine Vs, Is, and Rs. Let's just say we know exactly what they are. Okay? assume we determined Vs, Rs, and Is, right? So if I have like my black box over here, let's just say it is connected to some resistor RL. This is A, this is B. And let's just call voltage across this V out and current through it I out, right? If we determine Vs, Rs, and Is, I can replace this black box by either a voltage source followed by a resistor or a current source in parallel with the resistance. I can do that, right? So if we did this, we can replace the black box by either this guy, so Vs followed by Rs, and this is again point A and point B, or by this circuit. This is Is, this is Rs, and this is point A and B. Right? This is my black box. And obviously, this RL goes between A and B, so I can stick it back in here. So I have this RL, or in this case, I have this RL. Right? And since these two circuits are exactly the same, voltage across this is V out, current through it is I out. Current through this is I out, voltage across it is V out. Right? Because these are equivalent circuits. And we determined Vs, Is, and Rs such that these two circuits are exactly the same. Right? If we have this circuit, what is V out? We know this pretty well. What is it? It's a voltage divider, right? So value of V out is proportional to the value of RL. So V out is RL divided by RL plus Rs times Vs. Right? So as soon as I change the value of RL, you can simply just compute V out. You don't have to do anything else. But for a second, let's just assume this RL is much, much bigger than this Rs. Like, for example, RL is like 10K, and Rs is 1 ohm. What happens? Well, obviously, this term, RL, dominates this Rs because it's much bigger. So the denominator here is roughly RL, right? So this ratio is roughly 1. So my output is exactly the same as input, right? So if RL is much, much bigger than Rs, then V out must be roughly the same as Vs. How about I out here? What is I out? Again, that's a current divider, right? I know current through RL is proportional to the value of the resistance in other branch, which is Rs divided by Rs plus RL times Is. Right? What happens if Rs this time is much, much bigger than RL? Again, if I look at the denominator here, Rs dominates this RL, right? So the fraction over here is basically Rs over Rs, roughly, right? So I out is roughly Is. Right? And I out is roughly Is. What would have happened if Rs, in this case, the case of voltage divider, was much bigger than RL? It would be some number divided by RS, which is pretty huge. What is your output? Your output would be negligible, would be very, very small, right? Which again, that corresponds to this guy, right? That confirms this guy, which I out as roughly IS, right? If this V out is negligible, let's just say it's 0, what does it mean? It means that should be a wire there. If there is a wire over here, because I know V out in both circuits must be the same, right? So if in the current divider, V out is 0, what does that tell me? It means it's a wire there, right? And therefore, all the current that I have is going to flow through that branch, right? So these two things actually match. So it's just a matter of how we can compute this Vs, Rs, and Is. And if you can do it, then we're good to go. So next lecture, we're going to have like a methodical way of solving for Rs. We already know how to compute Vs. We already know how to compute Is. We're going to learn about like, Rs as well. And then no matter how complicated a circuit is, we can simplify it down to either of these circuits. And our lives are much, much easier. Any question? Any question? I'll see you guys Wednesday.